This video provides a brief introduction into the technique of topology optimization. It is deliberately held in a very simple and general way, hoping that it will provoke your enthusiasm for this design-driving technology. Up to this point you learned how to set up a linear static analysis. The results of such an analysis essentially provides you with information about displacements and stresses indicating whether failure will occur or not. If failure of the component is likely to occur, corresponding actions follow. Most of the time, material is then added in a step-by-step approach until the part performs in the desired way. Obviously, this is not only time-consuming, it also prompts the question, is the design optimal? Unfortunately, this question comes up quite late in the overall design process and project phase. Hence, employing structural optimization techniques such as topology optimization is not only changing the designs and design proposals. If used in the right way, it even shortens the design process as well. What does the optimization process look like? In fact, the process is rather straightforward, as you typically begin with a rather rough first CAD model. At that point, do not think too much about internal structures such as ribs, holes and so on. Just pay attention to the outer contour of the component, which essentially is restricted by packaging requirements. However, this first rough CAD model may contain areas or design details which shall not be changed during the optimization at all. What follows is the typical FEM analysis process including meshing, material definition, placing constraints, forces, and so on. Check the analysis results for any errors and warnings, as these issues will become part of the following optimization run. Also, the results serve as a baseline for the optimization. In other words, the results of this over-dimension part give you an idea about maximum displacements, stresses, eigenfrequencies etc. Then, the optimization setup starts. This includes the definition of the so-called design area, that is the area where the optimizer is allowed to change something. Of course, if needed, non-design areas may also be defined. Naturally, you need to define the objective of the optimization, such as minimize the mass or volume. You may also need to specify design constraints. An example may be, minimize the volume of the component as long as the displacements at a certain spot or area do not exceed the design constraints threshold. Optionally, manufacturing constraints, such as draw directions, member size, pattern repetition or grouping can be defined. After the optimization setup is complete, the iterative run is started. The optimized design resulting from the topology optimization is a conceptual result, which needs interpretation, followed by redesign in the CAD system and a reanalysis to validate the optimized design. I am sure, you will be thrilled by the process and its results. These are some of the most important optimization terms. Later on, while using the user profile OptiStruct for your research, you will come across panels named accordingly. Depending on your level of experience, you may skip the first part about the setup of a linear static analysis. This model will then be used for a simple, and quite restricted topology optimization within the process guide. There is not much user interaction needed here, as it is the intention of the demo to give you a feeling about this very. As in the other videos about the simplified FEM process, we first need to specify the user profile simplified FEM process. Then, we will rush through the setup of another linear static analysis. As mentioned above, this analysis will serve as a reference for the topology optimization. The setup of the linear static analysis model is briefly commented on. Hence, we shouldn't spend too much time on repetitions. And, of course, meanwhile, you are supposed to be quite familiar with the process guide and the associated working steps. check the model info in order to see what we just imported. Let's check out the geometry. Important to note, the imported geometry consists of two solids. As the thickness of the component was determined to be 5 mm, we choose 2.5 mm as our desired element, type in 2.5 and hit enter. We are using the standard values for steel. Remember, our unit system is newtons, millimeters and tons. The translational displacements of the three selected nodes will be constrained. In other words, their x, y, and z displacements are set to 0. We do not constrain the rotational degrees of freedom because solid elements do not have rotational degrees of these nodes will be constrained with respect to displacements in the y. And finally, these nodes are constrained with respect to displacements in the z.